Hello, Integrated Math 1. Welcome to Lesson 2.3.4a. Before we get too far into today's lesson, we do, of course, have a warm-up on page M2-203. Now, there are actually several of these there, but I just want you to do number 1. And all I want you to do is determine an ordered pair, x and y, that satisfies the inequality. So all I want you to do is come up with a number for x and a number for y that would make the statement true. That's all you got to do. Go ahead, hit pause, work this out, hit play when you're ready to check your work. Now, as you can imagine, there's actually a lot of right answers here, right? Because you're just looking for a number for x, a number for y that, if added together, would be less than 18. So you can pick a lot of different things. I'm just going to pick, 2 and 3, right? Because 2 plus 3, if I add those together, that's 5, which is less than 18. So that would make that statement true. I do need to write it as an ordered pair, though. It did say to determine an ordered pair. So fine, my x-coordinate is 2, my y-coordinate is 3, and there's the ordered pair. Again, not the only solution. It's a solution. You may have come up with something completely different, right? Maybe you came up with 5 and 6. Maybe you came up with 7.2 and 1.5. I don't know. You could come up with anything so long as added together they were less than 18. So this is an inequality that satisfies, this is an ordered pair that satisfies that inequality. So if we were to graph that inequality, that ordered pair would be on the shaded side of the shaded half plane of our inequality, right? That's the deal. Well, we've been solving, we've been graphing inequalities in two variables. But what if I have a system of inequalities, right? What if I'm working with a system of linear inequalities? So today we're on lesson 2.3.4a, just day 1 of systems of linear inequalities. So what happens when you have more than one? Oh my gosh. So we know a system of equations is more than one equation, and we know that the solution is where they intersect on a graph. So what does that mean for inequalities? So our goals over the next 2 days, we're going to represent constraints in a problem situation with systems of inequalities. If you don't know what we mean by constraints, don't panic. We will get to that today. We will write and graph systems of linear inequalities. So we'll write a system of linear inequalities, and we're going to graph that system as well and see what happens. And we're going to graph the solution to a system of linear inequalities in two variables as the intersection of the corresponding half planes. You remember before break where we said the solution to a system of linear equations was where they intersect. Same idea with inequalities, only they're not just lines anymore, they're entire half planes. So we're going to look for the section of the graph where they intersect, and we'll get in more detail on that in a little bit. And of course, we're going to verify solutions to systems of linear inequalities algebraically, like pick a point in the solution field, plug it in, does it work? Yay. So our key terms today are, of course, constraints and solution of a system of linear inequalities. So we're going to be playing with those terms today. So you've graphed an linear inequality in two variables, interpreted the solutions, right? That entire half plane, those are all solutions to inequality. That's everything that's greater than 18 or whatever it is. But what does the graph of a system of linear inequalities look like? And how can you describe the solution set? So to work our way into this, we have a problem scenario. We're river rafting. So Chase, we're on page 204, by the way. Chase is an experienced whitewater rafter who guides groups of adults and children out on the water for amazing adventures. The raft he uses can hold 800 pounds of weight. Any weight greater than 800 pounds can cause the raft to sink, hit more rocks, maybe maneuver more slowly. It just makes things way more difficult. So Chase estimates the weight of each adult as approximately 200 pounds and the weight of each child as approximately 100 pounds. And of course, Chase charges people money for this. So he has to be aware of the weight because he can't have more than 800 pounds in the raft or bad things happen. But of course, he charges people, right? This is a job. Chase charges adults $75 and children $50 to ride down the river with him. And his goal is to earn at least $150 each rafting trip. So we not only have to take into account they can only have so much weight in the boat, we also have to take into account that he's trying to earn at least $150 every trip, right? We have these two issues going on here. So let's write an inequality for each one, shall we? Starting with number 1 in your book there on page 204, can you just write an inequality to represent the most weight Chase can carry in terms of rafters? You might want to define your variables. Like for me personally, I said A is the number of adults in the raft and C is the number of children in the raft. That just helped me like set it up. So go ahead, hit pause, write your inequality, and then hit play when you're ready to check your work. So if you used X and Y, if you use something else, that's totally fine. I'm just using A and C, A for adults, C for children, because it was easy. Now, we're saying that we're talking about weight. And so I can see, grab my pen here. There's my pen. I can see that we can hold 800 pounds of weight. We don't want to go greater than that because it causes trouble. We're saying that each adult is approximately 200 pounds. Each child is approximately 100 pounds. So fine, adults, it would be 200 pounds per adult. So I'm going to say 200A. Plus, we've got the weight of the kids, right? Any kids that are in the raft. So plus, I'm going to say, what is that, 100 pounds? So 100C, so 100 pounds per child. Now, 800 is the max. That's the max. We can have less than 800 pounds in the raft. We can have exactly 800 pounds in the raft, but you can't go over that. So I need this total weight to be less than or equal to 800 pounds. I can have it be right at 800 pounds. We can have less than 800 in the raft. Just can't go over that, or it gets dangerous, right? We start putting people's lives at risk, and that's no good. Here, I'm going to erase this so you can see my pretty typed version. Ooh, so pretty. So we have an inequality for the weight. But remember that Chase was also trying to make money on this, right? Like he's trying to earn at least $150 each rafting trip. So can you write another inequality? And again, A for adults, C for children is fine. Can you write an inequality to represent the minimum amount of money Chase wants to collect for each rafting trip? Go ahead, hit pause, write your inequality, hit play when you're ready to check your work. So my first thought when I did this is I was like, okay, $75 per adult plus $50 per child. And we want that to be at least $150. So more than $150 is good, right? If he makes more money, that's a good thing. If he equals $150, that's a good thing. But he doesn't want to make less than $150. So this total should be greater than or equal to 150. So this is what I originally had, but then I realized something. Chase is one of the adults in the raft. So Chase's weight matters, correct? Right? Like he's one of the adults in the raft. His weight matters. However, Chase isn't charging himself. So I need to subtract out one adult for the price. We have to actually subtract Chase out of it because Chase's weight matters. So I need Chase to be one of the adults, right? I need him to be one of the A's. I need him to be one of the adults in the raft because he counts for the weight. But I don't want him to count for the money because he's not charging himself to go down the river. So for the money inequality, I realized I was like, oh, crud, I need to subtract out Chase. So I put a little -1 for the adult money. This is kind of messy. Let me show you the pretty one. I'm going to show you the pretty one. Ooh, there it is, all pretty. So this one looks a little different, right? It looks a little different because we had to remember that Chase is in the raft, but he's not being charged for it. So together, these are a system of linear inequalities that represents the maximum weight of the raft and the minimum amount of money Chase wants to earn per trip. So these two inequalities together, so our 200A plus 100C had to be less than or equal to 800, along with our other inequality about the money, so 75 times A minus 1 plus 50C is greater than or equal to 150. This, and oftentimes for a system, we'll put this little bracket on it so we know they're together, but this is a system of linear inequalities. So just like we've done before, where we had two equations and two variables which created a system of equations, we have two inequalities in two variables, which creates a system of inequalities. Yeah, and there we go. Again, I'll show you the pretty typed version since that's kind of the, let me erase that. Oh, there it is, all pretty and typed. Ooh, so nice. So we've created here a system of inequalities. Yeah. You don't have to use the bracket, but often we like to use the bracket. Now, in a system of linear inequalities, the inequalities are known as constraints. All right, this was one of the words from earlier. Inequalities are known as constraints because the values of the expression are constrained to lie within a certain region of the graph, right? When we graph inequalities, we know it's not the whole graph. We know it's that half plane or that half plane. So we call them constraints because they're being constrained within a section of our graph. One of the interesting things about systems of inequalities. Now, when we solved systems of equations, we said you could graph them, you could use substitution, you could use elimination, our favorite method. That's not true with inequalities. The only way to solve a system of inequalities is to graph it. It's the only way. And you'll see why in a little bit. In fact, let's work our way up to it a bit. We're on page 205 here. On page 205, for number 1, I have A and B, and I'd like you to consider 2 trips that Chase guides. And I want you to determine whether each combination of rafters is a solution of the system of linear inequalities and describe the meaning of the solution in terms of the problem situation. So first trip, trip A. Chase guides 2 adults and 2 children. Is that going to meet the weight requirement? Is that going to meet the money requirement? That's the question, okay? Go ahead, hit pause, see what you can do with this, and then hit play when you're ready to check your work. So first of all, Chase guiding 2 adults, that means we actually have 3 adults, doesn't it? And of course, we also have 2 children. So this means that A equals 3 because Chase is also in the raft with them, and C equals 2. Now, we were saying it was 200A plus 100C had to be less than or equal to 800. I'm just writing it up here so I have it for reference. And then we said, 75 times A minus 1 plus 50C. And we want that to be greater than or equal to 150. So we need these numbers to work for both inequalities. So I'm just going to plug into each one. 200, oh dear, don't be like that. 200 times 3, because I have 3 adults, plus 100 times 2. I'm going to grab my calculator and do some quick math here. 200 times 3 is, of course, 600, plus 100 times 2, which is 200. And that puts me right at 800. So we're okay because 800 is less than or equal to 800. I mean, it's equal to exactly, it's right on it, but we're good. So it's okay. So guiding 2 adults and 2 children, that works for the first inequality. Let's see if it makes them enough money. So for the money one, we said 75 times A minus 1, so 3 minus 1, plus 50 times 2 children. So we know 3 minus 1 is 2. If I double that, so 75 times 2 is 150, plus 50 times 2, which is 100. The lights in here, kind of dark outside already. It's a cloudy day. I'm getting nothing. I'm getting nothing. Oh, I'm getting blinded. 100 plus 150 plus 100 gives me 250. And yeah, that is greater than or equal to 150. So that's great. It works for both. Hooray. Let me erase all this and I'll show you the pretty typed version. So it works for the weight. Great. 800 pounds is we're okay on the raft. And it works for the money. $250. Yeah, that's more than the 150 that he said he wanted to at least make. So yes, this is a solution of the system of linear inequalities because the number of adults and children results in a true statement for both inequalities. So now that you've got the idea, check out the second trip. Chase guides 5 adults. Go ahead, hit pause, see if it's a solution. Hit play when you're ready to check your work. All right, so there's no kids, right? No kids. But remember, Chase is on the boat with the 5 adults, which means that there's actually 6 adults on this trip, no children. So let's check the weight requirement first. 200 times 6 adults plus 100 times 0. Of course, 200 times 6, if you have a handy-dandy calculator, is 1,200. 100 times 0 is 0. So that's 1,200. Oh, dear. That is not less than or equal to 800. Boo. Too much weight on the raft. That was way too much weight on the raft. That would be really dangerous. If you want, you can also, of course, check the money. What was that? $75. Whoopsie. $75 times 6 minus 1 plus 50 times 0. 6 minus 1 is 5. I need my calculator. 5 times 75 is 375 plus no kids. So, I mean, the money works. It's $375 is greater than or equal to 150. But remember, in order to be a solution to the system of equations, it has to work for both. And it doesn't. It doesn't work for the weight. Yeah, we'd be making a lot of money, but it's not much good if you're dead because the raft sank and y'all drowned because you put too much weight in the raft. So let me bring up the pretty typed version. I'm going to bring up the pretty typed one. There we go. Yeah, this is not a solution to the system because while it does satisfy the inequality for the money, it does not satisfy the inequality that represents the weight requirement. And so this isn't a solution. This is not a solution. It's not something Chase should be doing. Now, let's graph them. Now, don't freak out about graphing them. You know I'm going to help you. You know I'm going to work with you. Please notice that they made the adult rafters. A is like my Y. Okay, did you catch that? The adult rafters are like my Y-axis here. And my child rafters, actually, I think I got that backwards. It looks like my adult rafters are the X. So I'm gonna write this better because this is weird. I'm gonna say the adults are X, and my children are Y. Children. So here's what we're gonna do. These are hard to graph like this. So you know what? Can we solve for C? Can you just take a minute, go ahead and hit pause. Solve each of these inequalities for C. It'll make it a lot easier. And then we'll work together on graphing them. So go ahead and hit pause, solve each of these for C. We'll graph them, we'll get you sorted. All right, so real quick, I'm going to solve for C. So if I have 200A plus 100C is less than or equal to 800, I'm going to start by subtracting 200 on both sides, 200A I should say. So I have 100C is less than or equal to negative 200A plus 800. I'm going to divide by 100, and everybody gets divided by 100. And you'll see how nice this makes it, actually. So I have C is less than or equal to negative 2A plus 8. Oh, that's easy to graph. That's easy to graph. So I'm going to graph that. My y-intercept is 8. Pew. My slope is 2 over 1, so down 2 over 1. And I will connect the line and make the magic happen. Hang on. Boom, there's my line. It is a solid line because there is an equal sign. This says that C is less than or equal to it. So which half plane should we be shading, guys? That's right. We got to shade below the line. So I'm going to shade the entire half plane below the line. Yay. Let's solve the other inequality for A. And just to make it easier to see what I'm doing, I am going to use another color here. So I have 75. Let's go ahead and distribute this. I think that's a good call. 75A minus 75 plus 50C is greater than or equal to 150. I'm going to start off by adding 75 to both sides. That feels like a good idea. So now I have 75A plus 50C is greater than or equal to, thank you, Mr. Calculator, 150 plus 75 is 225. And we'll subtract 75A on both sides. I'm running out of space. It's okay, I'm going to write it over here. So I have 50C is greater than or equal to negative 75A plus 225. Wow, I got a hot mess going on here. And we'll divide everybody by 50. Sorry, that went weird. I'm going to leave this as I'm going to simplify it, but I'm going to leave it as a fraction. I'm going to divide both of these by 25, right? So that means I have C is greater than or equal to negative 3/2 A plus, I think I get a decimal here, but that's okay. It's not a bad decimal. I get like 4.5 plus 4.5. That's still pretty easy to graph. I grab my red pen again. So my y-intercept is 4.5, so about there, right? About halfway there. My slope is negative 3 over 2, so down 3, 1, 2, 3 over 2, 1, 2. And get my other point on. Solid line, right? Does have a squashed equal sign, so a nice solid line on that will be good. And this says that C is greater than or equal to that. So that means I need to shade everything above the line I just made. Now, this is a big fat hot mess, as you can see, but we've graphed it. Now, do you notice there is this narrow sliver where they overlap? You remember the solution to a system of equations was where the graphs intersect. Still true. The solution of a system of linear inequalities is the intersection of the solutions to each inequality. So every point in the intersection region satisfies all the inequalities in the system. So we shaded that side, but notice we have this sliver in the middle where it overlaps. That overlapping section is where all of the solutions are. So it's interesting because the solution isn't a single point, right? The solution isn't one single answer. It's everything in this little overlapping sliver. Everything in this overlapping sliver is a solution. Yeah. So here's what I would like you to do. Now that we know this, now that we know the solution of the system of linear inequalities is that intersection, that sliver and that chunk in the middle where they overlap, can you identify 3 different solutions of the system of linear inequalities you graphed? And what do the solutions represent in terms of the situation, right? How many kids, how many adults, all that kind of stuff. So I just want you to pick some points in the overlapping sliver and tell me what they represent in terms of the solution. Go ahead, hit pause, pick some points in the sliver, and then hit play when you're ready to check your work. So I picked a couple different points, and you may have picked different ones for me, and that's okay. So I picked this point right here. It's inside my sliver. That's what looks like we're counting by twos on this graph. So 2, 2, great. There's a solution. Yay. I also picked this one. It's in the sliver on the solid line. Sweet. So 2, actually, I don't want that one. I don't want that one. Let me erase it. I guess it'd be okay. I'm going to pick 2, 3, right? That's like right in the middle. Boom. So 2, 3. So over 2, up 3. And you know what? I think I can go 3, 1, right? If I go right there, through over 3, up 1, that's a solution. Sure. So I could take 2 adults, 2 children. Chase could take 2 adults, 3 kids. He could take 3 adults, 1 kid. So all of these will work. Yeah, these are all possible solutions. Can you determine a combination of adults and children from this graph that is not a solution for the system of linear inequalities, and explain why? Go ahead and hit pause. Give me a non-solution, and then hit play when you're ready to check your work. So I want something not in the sliver. So if I pick something like, I don't know, like 2, 1, like I know it's just barely outside of it, but that's not in my sliver, is it? That's not within the overlap of my graphs. So 2, 1 would not be a solution because Chase, one other adult and one child, would earn less than the $150 that he wants to earn. Yay. So now that you get the idea, now that we've got the idea, here's what I would like you to do. I would like you to determine the solution set of the given system of linear inequalities. So on page 207, I have 2 inequalities here. I want you to graph them and find the solution set, right? Where do these inequalities overlap? You might want to start by solving for y. Go ahead, hit pause, work this out, and then hit play when you're ready to check your work. So the first thing I did, just to make them easier to graph, is I solved for y. So I have x plus y is greater than 1, so I subtracted x from both sides. And I have y is greater than negative x plus 1. You may even want to put a 1 over 1 on that. Just makes it easier. So I have a y-intercept at 1. My slope is down 1 over 1. Oh my gosh, it got dark in here. Sorry. And I will connect my dots. Now, it should be a dashed line, if you recall. It's not equal to, so that's going to be a dashed line that's going to come through here. It says y is greater than all this stuff. So y is greater than, I got to shade the upper half, right? So, shaded. Let's go ahead and do this for the other one. I have negative x plus y is less than or equal to 3. So I'm going to go ahead and add x to both sides just to get my y all alone. So if y is less than or equal to x plus 3, and again, you could put a 1 in front of it, over 1. So it looks like my y-intercept is 3, 1, 2, 3. My my slope is 1 over 1, so up 1 over 1, and it's going to be like over here now. And of course, I need a solid line this time, right? I need a solid line because that is an equal to sign. So boom, there it is. And this is that y is less than or equal to my x plus 3. So I need to shade the half plane underneath the solid line. So I will shade away. Yay. And of course, this intersection is my solution. Yep. This intersection right here, this is our solution. All of these are solutions to this linear inequality. You can pick any point in this overlapping section and it'll work for both inequalities. That's a lot of solutions. I am going to make you think just a little bit here on page 208. Alan makes the statement about the intersection point of the system of inequalities. And I want you to explain why Alan's statement is incorrect. Hit pause, read Alan's statement, tell me why it's incorrect, and then hit play to keep the discussion going. So Alan says the intersection point is always a solution to a system of inequalities because that is where the two lines meet. Well, that's great if both lines are solid. But what if one of the lines is dashed? We know it's not a solution, right? It's not equal to. So that's why Alan is wrong. Alan is incorrect because the intersection point is not always a solution to the system of inequalities. Like the intersection point for this system that we just did, let me come back here, -1, 2, they do intersect right there, but it's not a solution because while this is solid, that one's dashed. It's not equal to. So it only works for one of the equalities, not both, and that means it's not a solution. So if the inequality symbols are not both equal to, if they're not both solid lines, then the intersection point is not a solution. So watch out for that. I've got just a few more of these. Now that you've got the deal, now that you know how this works, I have just a couple more of these. I think I only have like 2 more. Can you go over to page 209? I would like you to solve each system of linear inequalities by graphing the solution set and identify 2 points that are solutions of the system. So go ahead, hit pause, work out A, work out B, and then hit play when you're ready to check your work. So let's start with A. I have a y-intercept at 3. Boom. I have a slope of 5, and if you need to, you can put it as 5 over 1. So I'm going to go, where am I going to go? I'm going to go up 5, 1, 2, 3, 4, 5, and over 1. Boom. And, dashed line. Y is greater than, so I need to shade the half plane above. Yay. For this other one, I have a y-intercept at -3, so boom. I again have a slope of 5 over 1, so 1, 2, 3, 4, 5 over 1, boom. Again, a dashed line. But this says y is less than 5x minus 3, so we need to shade everything below the line. So I'm going to shade the half plane on that side. Oh, wait a minute. They don't overlap. There's no intersection. So guess what, guys? No solution. That's right. The solutions of each inequality in the system don't intersect. There's no solution. What? Yeah, that just happened. Okay, fine. How'd you do with this one? Did this one freak you out a little bit? Were you like, there's no y's? That's okay. That's okay. We can still do this. So x is greater than or equal to -5. Well, here's -5, so I'm going to put a little dot there. And if x is greater than or equal to it, that means everything to the right is fair game. Now, it does say equal to, so I'm just going to make a solid line here and just be like, everything to the right, because x is greater than. And that means I can do something similar with this other guy. X is greater than or equal to 1, so here's 1, and everything greater than that, so everything to the right. So I'll just make a line here, again, a solid line because of the equal to, and shade everything to the right. We have a big overlap. So if you want to identify 2 points that are solutions, pick any 2 points over here. I'm going to pick, let me grab my pen. I don't know. I'm going to pick this point. That seems like a good point. So 2, 0 is a solution. It's in the overlappy bit. I'm going to pick another point. Like, I don't know. I'm going to pick like this point. That sounds good. That's what, 5, 5? Sure. So 5, 5 is also a solution. There's a lot of solutions. You could have picked any points. Any points in the overlapping field is, of course, a solution. As always, guys, I hope you found this helpful. Hope you found this useful. If you got questions or concerns, come talk to me. I'm around, and I'll see you guys soon. Bye.